Hello all and welcome to the class on model evaluation techniques. So basically what we learned so far, I can just specify to you over here. Basically we learned that in machine learning we have supervised approach and unsupervised approach. Okay, and the difference between these two is that in supervised approach you have a target variable which is continuous. Your target variable is continuous, whereas in unsupervised approach your target variable is categorical. Okay, so under supervised approach we spoke about regression and classification, and we learned about the first form of algorithm, that is linear regression, and in classification we learned logistic regression. Okay, so apart from linear regression we also have certain regression algorithms such as decision tree, I would say decision tree regression, random forest. Okay, and these algorithms are even present in your classification, such as decision tree classifier. In regression we call it as a decision tree regressor, whereas in classification we call it as decision tree classifier and a random forest classifier. Okay, so as you move on in machine learning 2, machine learning 3, you will see that there are a lot more algorithms coming, but the question is which one to use. Can we use all these algorithms all the time? Let's talk about an example. Let's talk about an example of our very old ice cream sales. Okay, but you may not know much about decision tree or random forest. For the time being, I'm keeping it as simple as possible so that you can look at the things in linear regression point of view. Okay, so for ice cream sales, let's talk about, we have three models. One is the linear regression, then we have decision tree regressor and a random forest regressor. In order to predict the ice cream sales, that is the temperature versus ice cream sales, we did three models. Okay, and for this, for a given particular temperature, the linear regression said the ice cream sales would be 50. The decision tree regressor said it is 51. The random forest said it is 46. And many other algorithms which give their own predictions such as 51, 45, 40, and so on. Okay. Now, even though I was able to predict, in business, we can only rely on one number. I cannot use multiple numbers. I can only rely on one number. Basically, if we are able to see which algorithm is the most useful, so we can simply use that algorithm. So the model evaluation is the theory behind how can we choose the best model among multiple models. Now, speaking of model, what do you mean by a model? Speaking of model, what do you mean by a model? Does this mean an algorithm? Is model an algorithm? Not particularly. Basically, a model means a particular equation. Particular equation derived from an algorithm. Okay. So to give you a clarity, I can say logistic regression with probability of 0.5 versus a logistic regression with probability of 0.65. So now these are the two instances of the same algorithms. Okay, now basically these are called as the models. I have model 1 and my model 2. Okay, so let's get into what do we have in the session today. Now basically you have observed that the regression and classification are two different kinds of problems, and thus we have two different methods of evaluating these algorithms. Okay, in regression we will talk about the RMSE, the mean absolute error, the mean squared error, and we have something called as R squared error and adjusted R squared error. Okay, whereas in classification we have accuracy, confusion matrix, precision and recall, F1 score, EUC ROC curve, and classification report. So basically once we complete regression, only then we move on to classification. Okay, now let's start with the regression, the evaluation of a regression model. Okay, now basically when I talk about regression, it is nothing but curve fitting. Regression is nothing but curve fitting. Okay, regression is nothing but curve fitting. So to explain this regression, we always start with the scatter plot. So let's do it. I have scatter plot where on the x-axis I have my explanatory variable, and on the y-axis I have my target variable, and I have all the points scattered out and a best fit line passing through maximum points. So in regression we basically fit a line into the points. That is, the line fits into the passes through maximum points. That is, we hypothesize a causation. That is, y is depending on x. That is, y depends on x. This is our hypothesis. Okay. Now the question is, how do we check it? How do we check it? How do I check if this line is a good or a bad line? How do I check if this is good or a bad? So we realized in our earlier discussion that one of the good ways to know is by knowing the error. Okay. Now let's take an example. Let us say, let us create a hypothesis, a algorithm of our own. I would say y is equal to 2x. And to evaluate this, I would have my x, okay, and my y, which is actual. Okay, let's say I have 2, 3, 4, 5, 3, 4. These are my explanatory variables. Okay, and my actual y, it could be 6, 9, 9, 11, 8, 7. Okay, now for prediction, I have this equation, that is predicted y is nothing but 2 times the x. I have 4, 9, 8, 10, 6, and 8. Now, as we said, we calculate error, that is y actual minus y predicted. So 6 minus 4 is equal to 9 minus 9. No, it's supposed to be 6. Sorry. This is 2x, 3 to the 6. So 9 minus 6 gives me 3. 9 minus 8 gives me 1. 11 minus 10 gives me 1. 8 minus 6 gives me 2. 7 minus 8 gives me minus 1. Okay. Now, how can we summarize this error? How can I summarize this error? Can I take the average? I'll take the average, that is, error is nothing but summation e divided by n. It is 2, 3, 5, 6, 7, 8, 9, and minus 1. That would be 8 divided by, we have 6. Now, I have my average error as 8 by 6. Sorry. Now, is this good or bad? Is this a good approach or a bad approach? Let me take an example. Let me take one more example. Let's say minus 2, minus 3, plus 1 plus 2 plus 2. So basically, when I want to calculate error, this gets cancelled, minus 3, and this gets cancelled with this. I get my error as 0. That is, my average error is nothing but 0. But is the error actually 0? But is the error actually 0? The answer is no. We may feel that looking at average error, there is no error at all. But the error is present. In each and every line, we have error present. So this basically, this issue is coming from sign. The sign, the plus or minus sign we have along with the error. Okay. So we understand that taking average error is not feasible. When you take average error, we have issue with the sign. So instead of taking average error, let us take the absolute values of error. That is nothing but I take the absolute value of error. So this will be 5, 6 and 10. It will be 10 divided by 5. Okay. Now, when I take average error, when I take the absolute error, I resolve this issue. We have solved the solved the issue of sign in error. We had the problem with error is the sign, the plus and minus sign. By taking absolute, we have solved it. Hence, I would say the mean absolute error is more reliable or more realistic than your average error. But now, let me tell you about a problem. Okay, let's talk about a problem in mean absolute error. So in linear regression, when we build model, okay, the method was to find minimum error. So the error was differential. The error was differential to 0. Okay. The problem was this error function with respect to betas is supposed to be look like this. It should look something like this. whereas the mean absolute error, okay, what we defined just now will actually looks like this. Okay, it actually looks like this. It has a sharp point. Therefore, this error cannot be differentiated. We cannot differentiate this. Mean absolute error is a very good approach. Okay, but it cannot be a stepping point for development. Therefore, this development, this development happens in the next slide, that is your mean squared error. Okay, mean squared error. Let me explain you over here. So basically what we did so far was we took the error, we took the absolute value, we took the mean of it, that is mean absolute error. Okay, and with this we eliminated the problem of sign. But while trying to eliminate this problem, it gave rise to a new problem, that is I have sharp point. Okay, while differentiating I have a sharp point. Now let us work on an example to understand mean squared error. Let me do it here. Let's say I have my x, I have my actual y. Okay, let's say I have my predicted y. Okay, x could be, you can take the same example as before. It is 2, 3, 4, 5, 3, 4. And the absolute was 6, 9, 9, 7, 8, 7. And here we had 2x, so 4, 6, 8, 10, 6, 8. Okay, and let us calculate the error, that is actual minus predicted 2, 3, sorry, 1, 1, 2 and minus 1. Okay, now instead of taking the absolute value, let us square it. 2 square is 4, 9, 1, 1, 4 and 1. Okay, now when I do the average, now when I take the average, it's going to be 10, 14, 15, 20. It's going to be 20 divided by 6. It's going to be around, I think 6 3 is 18, 3.33. This is mean squared error. Hence, now with this, we have solved the problem of sine and also the problem of sharp edge. Due to square, due to parabolistic nature, I have my curve, something like this, which is different. It can be differentiated. Okay. Now, with this error, I also attract a problem. Okay. Let me explain the problem with the help of an example. If you can remember the house price example, that is, I have my square feet versus the price in rupees. Okay, I have something like this. When I calculate my error and square it, the error is nothing but y actual minus y predicted, where actual is in rupees lakh, predicted is in rupees. But when I take the error, that also will be in rupees. But when I square this, I have rupee square. Although we have solved the problem of sign and shape, it gave rise to a new problem, that is square. It lost its value. It lost its meaning. You can say lost its meaning. Okay. This gave us the idea to bring the concept of root mean square error. Basically, we had the error. Okay, we took the square of it, we took the summation of it and took the average. This becomes mean squared error. And to eliminate the issue of sign, to eliminate the issue of the value, we had to take the square root. Basically, error, you square it, you take the mean of it, you put it under a square root. Okay. Now, with this root mean square error, we have solved all the three. The first issue was the problem of sign. Okay. The second issue was the the sharp point. Okay. Third issue was it had lost its meaning. We have solved all the three. Okay. Now, let me explain you with an example. What happens if there is a outlier in the data? What happens if there is a outlier in the data? I have this linear regression and the line passing between maximum points. Let's say I have an outlier here. Okay, let me give some points. Let's call it as 1. I'm calling this as errors. These are the error values. Okay, that means basically when I say 2, I have the distance of 2 units from the line. Okay, and with respect to this, I have the distance, let's say about 10 points, and again 2, and again 1, again 2, let's call it 2 again, 2. Okay, so 1 2 1 2 this time I have 1 here, and 2 and 2. Okay, now when I want to calculate the mean absolute error, if I take with outlier, if I have to take mean, that is 3 4 5 6 7 9 10 11, 11 plus 10, that will be 21 divided by, how many points do I have? 1 2 3 6 7 8, 21 divided by 8. Okay, now if I want to take out the outlier, it's going to be 11 divided by 8. Now, is there a difference? There is a difference when you say mean absolute error. Let's talk about RMSE. Okay, RMSE, basically I have to consider with, I have my error, I have to square it, and for without I will have 1 square by 8. Okay, now if I were to calculate this, let me quickly calculate. This is going to be 7.42. It's going to be about 3.8. Let's say 3.87. Okay. Now, do you see that there is a lot of difference when an outlier is present? There is a difference in the presence of, due to the presence of the outlier. But is this difference in our favor? The RMSE varies a lot when there is an outlier in the data, and this variation is in our favor. Okay, this outlier affects in our form. The algorithm gives much higher error in the presence of an outlier. Hence, that is the reason why RMSE has been very popular choice of finding error. Now, error is not the only way where we can evaluate a model. Okay, error is not the only way where we can evaluate a model. We also have something called as R square. Okay, I might have explained you in earlier class whereby in 1900 there was a survey to predict the house prices. Okay, we were unable to construct a proper algorithm, but we went with the best possible thing to do during 1900, that is to conduct a survey, go to each and every house and understand at what price they are selling their house. Okay, and then we had only one column, that is the price column, and we had the values. Okay, and with single column the best thing what we did was we took the average. Okay, we took the average and we realized that prediction of average is still not a good thing. We still not a good thing. We are still unable to explain why this variation is happening. Why somebody is selling the price at a very lower rate and why somebody is selling a price at a very higher rate. So the average, okay, we just average, we were unable to explain this variance. So this variance. Therefore, we constructed a different analysis in which we had the price as target variable and a few explanatory variables. Okay, and then our construction became something like this. I had my explanatory variable, that is square feet, and the price. Okay, and my linear regression line, and we had our total variance here. Okay, and understood that as the square feet increases, the house price goes higher and higher. But there is still a small confusion. The confusion on why somebody is selling the house at a lower rate. The house with the same square feet, why somebody is selling at a lower rate and why somebody is selling at a higher rate. And this variance we called it as unexplained variance. We were not able to explain this spread. Okay, in Excel sheet we calculated this unexplained variables through the variance in the error column. I hope you remember it. Okay, and we measure the total variance through variance in this target variable column. Okay, and what we are trying to explain was we wanted to build a better model by defining R square as my target total variance versus minus unexplained variance divided by total variance. And this is a measure of how good my model was, and it turned out to be R square. Okay, now this is just a recap. We have already covered it in the previous sessions in regression. So technically this R square should be between 0 and 1, and it is higher the better. Okay, technically it is the percentage variation explained. Now let's compare two models. Let's compare two models. I have X, I have Y, I have 1, 2, 4, 5, and Y is 2, 4, 4, 7. Okay, this is actual. Now I have my predicted Y is around 2.5, 3.5, 5, 6.5. Now I have the error, that is actual minus predicted. This is minus 0.5, this is 0.5, minus 1, and plus 0.5. Okay, I would call this as model 1. And on the other side, I have model 2. Predicted. Okay, and I have my error as 0, 0, 0, 0. I don't have any error at all. Okay, when I plot these models, I get this as my model 1 with respect to Y. Let's say I have these points. Now for model 2, I have the line passing like this. Sorry, passing like this. It is passing through all the points. This is model 2. Now you can observe from model 1 and model 2. I can say model 2 is overfitted. The concept of overfitting is that with respect to your train and test, the model will give out everything. The model will give out 100% results for your train data, and it gives out very poor results for your test data. Now this is called overfitting. Okay, and the opposite of overfitting is underfitting. Underfitting. In underfitting, what happens is that for train, it gives you very poor result, and even for test, it gives a very poor result with a lot of variation. If you find both models, the train and test, getting poor results, and there is a consistency in between the results, then you find that the model is not suitable for the data set. But if you have poor results for train and test, and there is a high variance, then I would say the model is underfitting. Okay. Now, in this case, my model is overfitting. Now here, this is my total variance. As you can see, I have my total variance in both my curves. So R square will be less than 1 for model 1, whereas for model 2, since there is no unexplained variance, my R square will be equal to 1. Okay. Now, according to R square, normally the concept of R square is that higher the better. We just told that when the value of R square is higher, it is better. That means, according to our theory, when R square is 1 and I have a model with R square less than 1, then this is better. But technically, it is not better. Okay. Therefore, the problem is R square prefers complications. R square prefers complications. Okay. Therefore, in order to overcome this, we have a new concept. We have a new term called adjusted R square. It's nothing but we do some adjustment in R square formula and we call it as adjusted from R square. Now, before we go to the formula, okay, let me quickly brief you something. Now, for straight line, I give the equation as y equal to beta 0 plus beta 1x. Okay. Now, let's say this is for the straight line. Now, when I have a single curve, the equation becomes y equal to beta 0 plus beta 1 x plus beta 2 x square. Okay. Now, in general, when I have this curved equation, my equation will look like beta 0, beta 1 x1, beta 1 x, beta 2 x square, beta 3 x3, and so on. In general, I can say beta p and x to the power p. Okay. Now, where p is the degree of my polynomial. I understand that this equation is overfitted, but just to have clarity, now P is the polynomial degree. Okay, now the formula for adjusted R square is given as 1 minus R square into n minus 1 divided by n minus p minus 1, where n is your number of data points. Okay, and p is my degree of polynomials, and R square is my R squared error. Okay, now the advantage of adjusted R square is that it penalizes complexity. It penalizes complexity. Let me show you with the graph. I have my x and y. I have my regression points, and the first model where y depending on x, and the second model y depending on x and x square. Since I have a curve here, it's going to be x square. Now for model 1, okay, that is y depending on x, we get, let's say I have some R square and some adjusted R square. So we realize that the model is not so great. So we move on to the next model. That is the second model, which y depending on x and x square. For this model also, I have R square, some R square, and some adjusted R square. Similarly, I can go on with x cube, x to the power 4. I'll have multiple models. So ideally for each model, we calculate R square and adjusted R square. Now, if you look at this formula, okay, you can try to understand as the number of models increases, how does this formula gets balanced. Okay, so we realize one thing is, as we increase the complexity, the R square is going to increase. So the R square will be in the order of, let's say, m1, m2, m3, m4. Okay, it keeps on, it will increase. So as I increase my complexity, my R square will go on increasing. Okay, it will reach 1. Now let's talk about adjusted R square. That is adjusted R square is equal to 1 minus R square into n minus 1 divided by n minus p minus 1. So As r square increases, this whole value will decrease. Okay. If this decreases, okay, when this decreases, 1 minus something will increase. 1 minus something will increase, and hence adjusted r square increases. But over time, what happens is, as r square is increasing, okay, the degree x square x cube, the p value is also increasing. Okay, but if p value increases, the adjusted r square decreases. Okay, if I had to show you on a curve, I have p, the adjusted r square, it comes something like this. This is the optimum point, the optimum value of adjusted r square. So as we move forward, the growth of r square has been very low, so degree is quite high. Hence, the adjusted r square decreases. So it gives an optimum point. Okay, for different models, if you plot this particular curve, you will get an optimum point where that is the best model or the best complexity you can go on for the model. So we can actually choose the model with maximum adjusted r square value. Okay, now with this, let us go on to the Jupyter notebook. You might remember this example. This is basically our linear regression notebook, whereby we spoke about the sales in units with respect to the advertisement in from newspaper, TV, and radio. Okay, we had solved this before. You can go back and watch the previous recording, and we had come up with this equation. Okay, now to evaluate the model, basically I have sklearn. From sklearn, I import metrics, and to calculate mean absolute error, I have metrics dot mean absolute error. Okay, I calculate it for train and test. To understand mean squared error, in the same manner, I have this function mean squared error in metrics. Okay, I calculate it and I print it for my data set. And for root mean square error, I do not have a direct function of R to find out RMSE. But what I can do is, since I have mean squared error, I take a square root, numpy np dot square root of mean squared error. I take a square root of this mean squared error to get my RMSE. Okay. Now coming to R square, you need not follow this particular method because this is directly derived from the equation as I showed in Excel sheet. But what you can do is you can import a function called R2 underscore score. That is nothing but it gives you R squared error. Okay, matrix dot from scalar dot matrix import R2 underscore score, and I calculate it for train and test, and I print it. I get my R square error as 0.89 and 0.892, almost consistent for train and test. To calculate adjusted R square, we do not have any particular function built in into Python. Basically, whatever the formula I showed you, I have converted that into a function here. We have built a function, and while evaluating model, we just call this function. We just call this function and I feed the data set. Hope these points are very clear to you, because evaluating a regression model is quite simple compared to evaluating a logistic regression model or classification model. Okay, thank you.